Well, now it's time to do some derivatives. Before we get to the actual derivative, I want to show you what the point is with these derivatives. Here's one application. So let's say that this function right here gives you the temperature at a point that's on the xy plane. So we don't really need the three-dimensional graph, but basically the idea is this area in here, it's 100 degrees no matter what. So that's like the ambient temperature. And then this is saying that at the origin, there's a heat source. So this could be like a metal plate. And there's fire under here that's 150 degrees. Now suppose that you go to the point 1, 1. So plug in a 1 and a 1. You even have a little calculator here to help me out. So it's going to be 150 and then E. And if I put 1 and 1, this is going to be 2. So to the negative 2 and then plus 100. So that's going to be 120.3 degrees. So at this point, it is 120.3 degrees. Now, since this is the heat source right here, if you move away from this point, or excuse me, if you are at this point and you move away from the origin, it's going to get cooler. But how fast? And if you want to cool off faster, which direction should you go? Since this is the XY axis, we could go in the X direction. So let's say you move in the X direction and you go over by just a little bit to 1.1. So that means the y stayed constant. It's just going to stay a 1, and then the x is going to move over by a 0.1. What's the temperature now? So that's going to be a 150, and then E is raised to a negative. Now I need 1.1 squared for the x squared, and then plus 1 for y. Then there's the ambient temperature of 100. So it cooled off to 116.455. So at this point, it's 116.455. So that means the change in the temperature, or the difference in the temperature, as x changes, because only x changed, the y did not, well, it went down by about 4 degrees. So let me say this minus the original 120.3. It went down by negative 3.8, or it went down by 3.8 degrees. But this says divide by dx. Well, dx is going to be a 0.1 because this went from 1 to 1.1. So divide by a 0.1. So the difference in temperature divided by the difference in x is a negative 38.449. Now let's find the actual derivative. So this right here is an approximation for the derivative. If I had used 1.0001, the number I get here would even be a better approximation for the derivative. So how do you find the derivative? Well, you can go in two directions. You can go in the x direction, or I could have gone in the y direction. This is going in the x direction. That's what this dx is saying. So to find the actual derivative, dt dx, the y is held constant. So only the x is moving. The y is staying the same. So when you take the derivative, you just pretend that y is a constant and that x is the variable. So the derivative of the e function will be the e function. And then there's the chain rule. So take the derivative of this. Well, the derivative with respect to x, the derivative right here is going to be negative 2x. And because this is a constant, the derivative is 0. So the derivative of that exponent is going to be negative 2x. And the derivative of 100 is 0. So then, evaluating the derivative at the point 1, comma 1, so at this point right here, that would be 150, and then plug in a 1 and a 1, so this is going to be 2, e to a negative 2, and then times negative 2. And then we get to see how good was our approximation right here. So 150 e to a negative 2, and then times a negative 2. And the actual derivative is negative 40.601. So that's saying if you're standing at this point, the moment that you leave, the temperature is going to be dropping by 40 degrees as you go in the x direction. Then what about in the y direction? So now take the derivative with respect to y. So that would mean, what if you go in this direction? Is it cooling off faster or not? So when you take the derivative with respect to y, then x is going to be a constant. To begin with, the derivative of the e function will be the e function. Then do the chain rule. Since this is being held constant, the derivative is 0. The derivative of y would be 1, so it's going to be negative 1. And then, to finish this one up, plug in the 1, comma 1. So, I forgot to write the 150 first. 150 e, and then if you plug in 1 and 1, that's going to be e to the negative 2, and then times negative 1. So really I just need to change this number, and it would be negative 20.3. So if you were standing at this point and you wanted to cool off faster, that would be this one. It's cooling off by 40 degrees. This one's cooling off by 20 degrees. So if you want to cool off fastest, then go in the x direction. That is the idea of partial derivatives. Then for a little bit of notation. So if you have a function f and you take the derivative with respect to x, well, in Math 3a, we would just call that f prime. But in Math 3c, this is not telling you what the variable is. So the notation for this is just f with an x at the bottom. And for the derivative of f with respect to y, so if it has two variables, it has two first derivatives. For the next example, let's say the function of x and y is equal to xy cubed plus y e to the x squared. And then there's going to be two derivatives, so we need two parts. Part A, find the derivative with respect to x at the point 1, comma 2. And then we'll do it with respect to y. So take the derivative with respect to x. So the y's will just sit there and you pretend they're a constant, like a 7 or something like that. So the derivative with respect to x, the derivative right here with respect to x will be a 1. And the y cubed is constant, it just sits there. Same with this y right here. And the derivative of e to the x squared is e to the x squared. And then due to the chain rule, take the derivative of this x squared, which is 2x. And then plug in the 1 and the 2. So you can say take the derivative and plug in the number 1 comma 2 with this notation. And this notation means the same thing. Take the derivative, evaluate it at 1 comma 1. So that just means plug in the numbers. So this will be 2 cubed plus 2, and then e to the 1 squared, and then 2 times 1. So that's going to be 8 plus, and then this would be 4 times e. So this is 18.873. This could also be used, for example, in a business situation. Suppose their business, perhaps it's Apple Computer Company, by which I mean Apple, comma, a computer company, because their name is Apple. Anyway. And they have iPhones and they have Macs. So this is saying, and this function right here is going to give them their profit. So how does their profit change? So that's what the derivative is saying. How does their profit change if they change the number of iPhones? And if they sell 1 million iPhones and 2 million Macs, then they'd be making $18 million. So anyway, there's applications like that. Then for part B, find the derivative with respect to y at the same point. So now the x's are going to be considered constants. So I'm just taking the derivative of this, and then I'll take the derivative of this. So the derivative with respect to y will be the x just sits there, and now take the derivative of this y cubed. So that's 3y squared. And then the derivative of this y is going to be a 1. And then e to the x squared just stays there. And now plug in the 1 and the 2. So x will be a 1, y will be a 2, x is a 1. So this is going to be 4 times 3, so that's 12 plus e to the 1. 12 plus e to the 1. So their derivatives are different. For the next example, how about some trigonometry? Suppose that z equals x times sine of x times y. What's the derivative with respect to x? Now this is a product and it has x in 2 different places. So then we need to view it as the product rule. So take the derivative of the first function, that's going to be a 1, and then leave sine alone. Plus the product rule says leave x alone, and now take the derivative of sine. And the derivative of sine is cosine. Then we need to do the chain rule, take the derivative in here. So the y will just sit there as a constant. Since we're taking the derivative with respect to x, this will be a 1 times y. So that's the derivative with respect to x. The derivative with respect to y, so this one does not require the product rule because this is just like having a 5 out here. And if this is a constant, when you're taking the derivative, you just go ahead and take the derivative of sine, and this constant will just sit there. So the x just sits there. The derivative of sine is cosine. And then the chain rule. So take the derivative of this y, which is going to be a 1, and it'll be times x. And there are the first derivatives. Next up, what about second derivatives? So you can have the first derivative with respect to x, and you can have the first derivative with respect to y. Now, for the second derivative, take the derivative of the derivative. Well, since this function could have x's and y's in it, that means you have to take the first derivative and now take the derivative with respect to y. Then you have to take the first derivative and now take the derivative with respect to x. So there's actually going to be 4 second derivatives. So for the second derivatives here, you would have the derivative with respect to y, and now take the derivative with respect to x, then take the derivative with respect to y, the first derivative, and take the derivative with respect to y. You may remember in Math 3a, the second derivative will tell you if it's concave up or concave down. So this shape right here is concave down. The second derivative would be negative. And in Math 3a, if the second derivative is positive, then it's concave up. Well, something similar is going to happen. We're not going to do it in this section right here, but something similar is going to happen with the second derivatives, except you don't just have one second derivative to consider, you have 4 of them. So now let's practice finding the second derivatives. So for the next example, suppose the function is x squared minus x times y cubed. So the derivative with respect to x. The derivative right there will be 2x. The derivative right here will be 1, and this is a constant, so it just stays there. So minus 1 times y cubed. There's the first derivative with respect to x. Now find the first derivative with respect to y. Well, this is considered a constant, so the derivative of that is 0. The derivative over here will be 3y squared, and this will just stay there. So there will be the negative, there will be 3y squared, and the x will just sit there. Now for the second derivatives. So this is the first derivatives, and now for the second derivatives. So the derivative with respect to x, you now take the derivative with respect to x again. So this is a constant, the derivative will be 0. The derivative with respect to x on this one is going to be a 2. Next, take the derivative with respect to x again, and this time take the derivative with respect to y. So if we're taking the derivative with respect to y, this is a constant, so its derivative is 0, and the derivative right here will be negative 3y squared. Okay, we've got 2 out of the 4 second derivatives. Now move over to this one. Take the derivative with respect to y, and now take the derivative with respect to y. The order that you do these really doesn't matter, but I do like to work from the first derivative and then do the 2 second derivatives, then do the derivative with respect to y, and then do its 2 second derivatives. But whether you do xx and then xy, or you do xy first and then xx, that doesn't really matter. Okay, so we're taking the derivative with respect to y. So this is constant, that'll just sit there. The derivative of this is 2y. So I could put that 2 together with this, and it's going to be negative 6xy. Now take the derivative with respect to y, and finally take the derivative with respect to x. So that means that this is going to become a 1, which leaves negative 3y squared. Ta-da! There are the second derivatives. Notice, quite often, these two turn out to be the same. Not every time, but quite often turns out that these two are the same. Let's try another one. How about z is equal to tangent of x plus x squared y. Find the second derivatives. So the derivative with respect to x. The derivative of tangent is secant squared. The derivative of this will be 2x, and the y is constant, it just stays there. Now take the derivative with respect to y. Since this is considered to be a constant, its derivative is 0. The derivative of this will be a 1, and this constant will just sit there. So this is 0, this is 1 times x squared, so that first derivative is equal to x squared. Now for this one, take the derivative with respect to x and take the derivative with respect to x again. So for this one, I need to take the exponent of 2, bring it down in front, multiply, and then subtract 1 from that exponent. Then take the derivative of what's inside that square function. The derivative of secant is secant of x, tangent of x. And then over here, the derivative of x is 1. Excuse me. So it leaves behind plus 2y. For the other second derivative, start with the derivative with respect to x, and now take the derivative with respect to y. That's a constant, so the derivative is 0. The derivative right here would be 1, and so it's going to leave behind 1 times 2x. All right, now do the z, y. So take the derivative with respect to y. Since this is a constant, its derivative is 0. Then take the derivative of y with respect to x. And the derivative of this with respect to x is 2x. And once again, those two turned out to be the same. All right, just 2 more examples. The function is equal to x cubed plus y squared. So this, I pretty much stole from the homework. And so far, it looks like it's not going to be any different than what we've done before. But check this out, the directions. Find slope of the tangent line at 1, 1. So slope of the tangent line, if we're in Math 3a, you would just take the derivative and you would plug in these numbers. But in here, it's not saying with respect to x or with respect to y. That's because the sentence isn't finished. So it needs to be at this point, and then it's in the plane where x equals 1. So that means that x is a constant. So that means that we need to take the derivative with respect to y, because they're literally telling us that x is a constant. The derivative with respect to y would just be 2y. So then all we need to do is substitute the number, and we would get 2 times 1, so the slope is 2. And there's just one more. So this one's a little bit different because this is an implicit function rather than an explicit function. All the ones before have been an explicit function. But what if you just have an equation? It doesn't say z equals. So that's the function. And it would be very difficult to solve for z, so we're not going to be able to do that. Find the derivative of z with respect to x evaluated at the point 1, 1, 1. So we need to take the derivative with respect to x. This means that z is a variable and x is a variable. So it's y that we're going to consider to be a constant. Since y is not mentioned over here, then it's not changing. So take the derivative with respect to x. Right here, that would be a 1, and the constant 2 and the constant y would just sit there. 2y. Now take the derivative of z squared. So this is implicit differentiation. So you would have 2z using the power rule, and then you would need to take the derivative of z. And since I don't know what z equals, I can't put its derivative right here. I can just say take the derivative, and that's what goes right here. Now, since this has both the z and x in it, we're actually going to have to do the product rule. So I've only done the derivative of this. Now I need to leave this alone. Now I'll leave the z squared alone and take the derivative of x. So that would say dx over dx, so that's just a 1. And then over here, the y is constant, so negative y stays there. And take the derivative of z, so that would be dz dx. And on the right side, the derivative is 0. Now we can plug in 1, 1, and 1. So this would be 2 times 1. This would be 2 times 1 times the derivative times 1. So that leaves 2 times dz dx. This would just be 1 squared. And then minus 1 times dz dx. Okay, so right here there's 2 derivatives of z minus 1, so that leaves just 1 derivative of z. And then 2 and 1 is 3, move that to the other side, it equals negative 3.